It feels like even with all the incredible leaps we've seen in AI, like you hit these limits.
Oh, absolutely.
You ask a really intricate question or something that needs super up-to-date info, and it's like you can almost see the AI straining.
Yeah.
Not always quite getting there, but what if we're actually on the cusp of a real game changer in how AI handles this kind of challenge?
I think it is. It really is this fascinating frontier, pushing past those inherent limits of like static training data
Yeah,
and giving these powerful language models the ability to like access and use information, but do it live, do it dynamically in real time.
exactly. And that is what we're going to be diving deep into today. We're looking at this super interesting research papers titled Search-R1, Training LLMs to Reason and Leverage Search Engines with Reinforcement Learning. And it's by Bowen, Jin, and a whole team of researchers.
Great team.
Yeah, really impressive stuff. Our mission today in this deep dive is to really unpack this Search-R1 framework, understand how it allows large language models to not just reason, but to really smartly integrate search engines into how they reason to become active learners. We're going to be going through this paper, breaking it down, and we've got some extra notes here just to really give you a clear picture of what makes this framework so innovative.
And it is a potentially transformative step, right? Because we've seen LLMs do amazing things,
Yeah,
but they're ultimately limited by the data they were trained on. So this ability to go out and grab new information, the most up-to-date information to solve problems.
right.
That's huge. It's crucial for tackling those more intricate real-world problems that demand current knowledge.
And it is because the current methods, they kind of feel like a bit tacked on, you know what I mean?
Yeah, for sure.
It's like we prompt an LLM to use a search engine during inference, but it's almost like an afterthought.
Right.
Or we've got retrieval-augmented generation, or WAG, which is a step forward, a bit more integrated. But Search-R1 seems to be aiming for something way deeper.
It is. It's a fundamental shift in how these models learn.
So let's unpack this for a second. Why isn't just saying to an LLM, go search for this, enough to get the best performance?
Well, it really boils down to the fact that the search behavior itself isn't being optimized.
Okay.
The LLM might not come up with the most effective search queries.
Oh, I see.
It might not know the perfect time to trigger a search in its reasoning process,
Oh, okay.
and it might struggle to really smoothly blend in that retrieved information.
Interesting.
It's like a fixed procedure applied only when you're actually using the model rather than a skill that gets honed through learning.
That makes sense. I guess it's like giving someone access to a massive library, but no real guidance on how to actually find anything useful in it,
Exactly.
or even know if what they're reading is any good.
Right, exactly. And then we have RAG, retrieval-augmented generation.
Yeah,
This is a more advanced strategy where relevant text snippets are pulled in based on the initial query, and they're given to the LLM as additional context.
right. And that's been a pretty big advancement, hasn't it?
It has, yeah,
Giving the LLM this direct access to outside information within its processing window.
absolutely. But the authors of this paper, they point out a few inherent limitations. One big one is retrieval inaccuracy.
Okay.
The search engine might return irrelevant or noisy information, which can then, in turn, mislead the LLM's reasoning.
So even with that extra step of retrieval, you can still get bad info and it can throw the whole thing off.
Exactly. And Jin et al., in their research from 2024, really addressed this challenge head on.
Okay.
And then another big limitation is dealing with these multi-hop questions,
Right.
the ones that made you to link information from multiple sources.
Okay.
The 2018 work on the Hotpot QA dataset by Yang and their team, it really brought this to light. RAG just often struggles to do multiple retrievals based on those intermediate stages of reasoning.
And this is even with those multiple rounds of prompting, like in a multi-turn RAG setup.
Well, even with that, the core issue is that the LOM isn't learning this iterative process of searching and reasoning during its training.
Oh, okay.
It's still this fixed sequence that happens only when you're using the model.
So it's not getting any better at finding the right information over time with these methods.
Exactly. Now, the paper also briefly mentions this idea of treating search engines like external tools that LLMs can use.
Okay.
While prompting can help guide this usage, it's often fragile. It might not generalize well to new situations.
Right.
And then you've got training-based approaches, supervised fine-tuning, for example.
Okay.
Schick and their team in 2023, they did some great work with Toolformer, which uses this approach, but it usually requires a ton of carefully labeled data showing the ideal search and reasoning path,
Right.
and getting and scaling those data sets. It's a massive hurdle.
Yeah, that makes sense. So we've got these existing techniques. They definitely offer benefits, but they don't achieve that really deep integration of search into the LLM's thought process.
Yeah.
and they don't let the LLM actually learn and refine its search skills over time.
Right.
This is where Search-R1 comes in.
Right.
This is a totally different approach, right?
Yeah, it is a completely different paradigm. It frames this problem as a lead enforcement learning task. So now the LLM actually learns through trial and error.
Okay.
It learns how to effectively work with a search engine to make its reasoning better.
So instead of being told when and what to search for, it's making those decisions on its own
Right.
and then getting feedback based on whether those choices lead to a right answer.
That's the core idea, yeah. It's autonomously generating these search queries
Okay.
as a natural part of how it thinks. And this whole dynamic, it's all learned through reinforcement learning.
Okay.
It's not a separate thing bolted on. It's woven into the LLM's decision-making process.
And the paper mentions that Search-R1 builds upon the DeepSeek R1 model.
Yes.
What were the big advancements in that model before they added the search element?
So DeepSeek-R1, described by Glow et al. In their 2025 paper, it focused on boosting the LLM's internal reasoning skills,
Okay.
using the knowledge it already had encoded, its parametric reasoning capabilities, through reinforcement learning.
Right.
Search-R1 takes that and then expands it by adding this critical ability to tap into external knowledge through search.
So it's like taking an already really good internal problem solver and then giving it the tools to go out and actively find extra information when it needs it.
Yeah, and it's learning the best ways to use those tools, too.
I like that analogy.
It is. It's a good one. And the real innovation of Search-R1 is in how seamlessly they've blended this search engine into the reinforcement learning framework.
Okay, let's get into those key innovations.
Okay.
The first one you talked about was making the search engine part of the reinforcement learning environment. Unpack what that means from a more academic standpoint.
So in Search-R1, the search engine isn't just some external utility the LLM calls upon. It's modeled as an active part of that reinforcement learning loop.
Okay.
The LLM makes a move. It could be generating some text or choosing to do a search.
Right.
And the environment, which now includes the search engine, responds.
Okay.
This design allows for this constant back and forth between generating text and doing search retrievals, all within a single interaction.
So it's not a think then search kind of thing. It's way more dynamic and fluid.
Exactly. And this framework, it's built to work with well-established RL algorithms like PPO.
Okay.
Proximal policy optimization from Schulman et al. In 2017.
Right.
And GPO, gradient reversal policy optimization from Xiao et al.'s 2024 work.
Okay.
The paper actually presents results using both of these techniques within Search-R1.
The second innovation is using these special tokens to help with that multi-turn back and forth reasoning in search. This seems like a really important part of letting the LLM actually orchestrate its search and thinking. How does this token signaling actually work?
So this is where the structured nature of the interaction becomes really clear.
Okay.
The LLM is trained to generate specific tokens that act like signals.
Okay.
They show what it's trying to do in that sequence of generated text.
Right.
When the LLM figures out it needs outside info, it generates a natural language query, but it puts it between these special tokens, search and search.
So these are like flags to the system saying, hey, I need a search right here.
Exactly. And when the system sees this search and search pair, it knows to grab that query and send it off to the search engine.
Okay.
Then the results that come back from the search engine, they're put inside their own special tokens, information and information.
Okay.
And that whole chunk is added to the text.
I see.
That retrieved info then becomes additional context for the LLM's next reasoning steps.
Right.
And those are marked by, you guessed it, more special tokens. Think and think.
Okay, so it's really clearly laying out its thought process and its info-seeking process, all within the text it's generating.
Precisely. And then finally, the answer itself gets formatted using, you guessed it, more special tokens. Answer and answer.
Okay, so these special tokens, they create this clear structure for the LLM to manage its internal reasoning and those interactions with the search engine.
Yeah, it's fundamental for that iterative decision-making we talked about.
Okay.
It can go through this cycle of reasoning, figure out where it needs more info, trigger a search, process that info, and then reason some more.
Right.
Maybe trigger more searches as needed until it comes up with the final answer.
Okay, the third key innovation is the outcome-based reward. You mentioned it's simple. Can you break down how this reward function is actually defined and why they chose this design?
So the reward function they use in Search-R1 is really straightforward. It's all based on whether the final answer from the LLM exactly matches the actual correct answer.
Okay.
Exact match, it gets a positive reward.
Right.
Anything else, zero reward.
So it's a yes or no, right or wrong kind of signal.
Exactly. They went with this simple outcome-based reward structure to avoid the headaches that come with trying to design process-based rewards.
Okay.
Trying to create rewards that accurately capture and encourage good intermediate steps in reasoning or searching, that's really hard to do.
Right.
It might not even work well for different tasks. They also wanted to minimize the risk of reward hacking.
What's that?
Well, it's something we see a lot when training neural models with complex reward signals.
Okay.
The model figures out how to exploit the reward system without really getting better at the core task.
Interesting.
This simple reward design, it aligns with what they found in that earlier DeepSeek R1 work too,
Okay.
which also used these sparse outcome-based rewards.
So the basic idea is if you reward the right outcome, a correct answer, the LLM will figure out the best strategies to get there, including when and how to use search. It's learning by consequence.
Exactly.
The simplicity is actually a pretty elegant choice then in this context.
It is, yeah.
Okay, the last innovation is retrieved token masking. This sounds like a pretty critical detail to make sure the reinforcement learning works well and stays stable.
It is, yeah.
Could you give a more technical explanation of how this technique works and why it's so important?
So during this reinforcement learning, the LLM is putting out a string of tokens.
Okay,
This includes its own generated stuff, like reasoning steps and search queries, but it also has the content it got from the search engine.
right.
Now, the RL algorithm uses a loss function over this whole sequence of tokens to update the LLM's internal parameters.
Okay,
But if you apply the same optimization process to those tokens from the search engine, the outside info, it can mess things up.
oh, okay.
The LLM's goal should be to learn how to use that retrieved information to reason better, not to try to change the content of those documents themselves.
So it shouldn't be adapting its internal representations based on the specific wording of what it finds?
Exactly. To prevent this, Search-R1 uses retrieved token masking.
Okay,
This means masking or hiding the loss associated with the tokens that came from the search engine during training.
okay,
So now the gradient updates, the adjustments the algorithm makes are mainly influenced by what the LLM itself generated.
right.
Its queries, its reasoning step, answer.
Okay,
This keeps the learning focused on optimizing the LLM's actions,
okay.
especially how it interacts with the search engine and then reasons with the info it gets back without getting sidetracked by the details of that retrieved content itself.
So it's like saying, we're teaching you how to ask the right questions and how to think about the answers, not about the answers themselves.
Precisely.
That makes a lot of sense. So with all these innovations in place, how did Search-R1 actually perform?
Really well. They tested it out on 7 different benchmark datasets.
Okay.
These included general knowledge question answering tasks like natural questions,
Right.
trivia QA and pop QA, as well as more challenging multi-hop tasks like hotpot QA, 2wiki multi-hop QA, musique, and bamboogle.
That's quite a range of tasks.
It is. They wanted to really put Search-R1 through its paces.
And what were some of the standout results?
Well, they saw substantial improvements when using Search-R1, especially compared to methods that didn't use this learned search integration.
Okay.
They reported significant average relative improvements in accuracy.
Okay.
26% for the QWen 2.57b model,
Wow.
21% for the QWen 2.53b model,
Okay.
and 10% for the LMA 3.23b model.
Those are big gains. That really suggests a real jump in the ability to use external knowledge.
It does, yeah. And importantly, these gains were consistent across in-domain and out-of-domain datasets.
So it's not just doing well on stuff it's already seen, it's generalizing.
Exactly. And the paper also compared Search-R1 to just a plain RL-trained model without the search.
Okay.
So they took their implementation of the R1 model from Guanal,
Right.
which uses similar RL techniques to improve reasoning,
Okay.
but without that search engine component.
Got it.
As you might expect, Search-R1 consistently did better.
Okay.
It really highlights how valuable that integrated search function is.
Yeah, that's a key validation.
It is, and it's not just for instruction-tuned models either.
Oh, really?
It worked well for base language models too, and across different LLM architectures,
Okay.
like QAT 22.5 and LMA 3.2.
So it's not limited to one specific type of model.
No, this broad applicability is pretty significant from a research perspective.
Right.
It suggests that this idea of search-augmented reinforcement learning, the way Search-R1 implements it, is potentially very generalizable across different LLM families.
That's fascinating.
It is, and the authors, they specifically contrast this with what we've seen in other areas, like mathematical reasoning,
Okay.
where how well RL works can depend heavily on the specific model you're using. Zeng et al. found that in their 2025 work, the
Interesting.
consistent gains with Search-R1 across all these different models, it points towards a more fundamental advantage in how LLMs can learn to interact with and use outside knowledge.
Now, the paper also looked at using different RL algorithms within Search-R1, PPO, and GPO.
Right.
What were the main differences they saw and how those trained and how well they ultimately performed?
They found that GPO generally learned faster than PPO. It
Okay.
converged faster during training. This
Right.
might be because of the different ways these algorithms update the model's policy,
Okay.
but they also noticed that GPO could be a bit unstable at times during training.
Okay.
PPO, on the other hand, tended to be more stable and reliable.
Okay.
Interestingly, even with these differences in training, the final performance levels they reached were often pretty similar.
Okay.
GPO sometimes even edged out PPO slightly on certain tasks.
So it's like a trade-off between speed and stability depending on the algorithm.
That's a good way to put it, yeah.
Okay. And they also look at using base LLMs versus those that have been instruction tuned as the starting point for Search-R1. What did they see there?
Well, as you'd expect, the instruction-tuned models learned faster and started off better.
Okay.
They already had a head start in terms of following instructions and doing different language tasks.
Right.
But what was really interesting was that the final performance of both types of models, base and instruction-tuned, ended up being pretty much the same after enough RL training.
So while instruction tuning gives you an initial edge, the RL process itself can really close the gap.
Yeah, it's powerful stuff. It shows that even a base LLM without any fancy pre-training can learn these complex search and reasoning strategies.
It highlights how much potential there is in just letting the model learn through experience.
Exactly.
Okay, I know they also analyzed how long the responses were that the models generated during training. What did that show?
Oh, that was interesting. They saw a very clear trend. Early in training, the responses got shorter,
Okay,
which probably means the model was learning to be more concise and cut out fluff.
okay,
Then, as training progressed, the responses got longer.
interesting.
That's likely because it was learning to use the search engine and adding in those retrieved bits of information.
Okay,
Finally, towards the end of training, the response length settled down.
okay.
It figured out its search strategies and how it wanted to weave in that external knowledge.
So it's almost like watching it figure out how to use the search engine effectively.
It really is. And this change in response length, it mirrored the improvement in the training reward,
Okay,
suggesting a link between being able to use search well, include those results, and ultimately generate correct answers.
that makes sense. Okay, and I know you mentioned the retrieved token loss masking. The paper also looked at what happens if you don't use that technique, right?
They did. It was an ablation study. They wanted to see how important it was.
Okay,
They compared training and performance with and without retrieved token loss masking.
okay.
And it was clear the masking made a huge difference.
Oh, really?
Training was way less stable without it,
Okay,
and the final performance, it was much worse.
interesting.
So it really underscores how critical that masking is.
It makes sure the RL process is focused on those LLM-generated actions.
Exactly.
Okay, and finally, they did a case study to really illustrate how Search-R1 works in a specific example.
They did, yeah.
What were the key takeaways there?
Well, it really showed how Search-R1 lets the LLM do a much more thorough and nuanced analysis of the problem.
Okay,
It used this back and forth process of reasoning and multi-turn retrieval
right.
way better than an RL-trained model without search could do.
Okay,
It showed how Search-R1 could break down a complex question into smaller parts,
right.
figure out relevant search queries, process that retrieved information well,
Okay,
and then refined its reasoning based on what it learned.
that's fascinating.
And even more interesting, they saw instances of self-verification.
What do you mean?
So even after it seemed like it had a good answer, it
Uh-huh.
would go and trigger another search just to double check.
Wow.
This echoes what Guo et al. Found in their 2025 work on reinforcement learning for LLM reasoning without retrieval.
Okay,
It suggests that RL can encourage this kind of self-critical, verification-driven reasoning even when using external knowledge.
so it's not just about finding the information, it's about being a more careful and reliable reasoner by actively checking what it knows.
Exactly. It's a big step towards AI that we can depend on.
So to sum up this whole deep dive, Search-R1 is a significant leap forward.
It is.
It's not just about getting LLMs to use search engines.
Right.
It's about teaching them how to search effectively as a core part of how they think.
Right.
Using the power of reinforcement learning, those key innovations we discussed, making search part of those structured interactions, that outcome-based reward, and the token masking, they all work together to create this new way of learning.
It is a novel learning paradigm, really.
And those huge performance gains across so many tasks, plus what we're learning about training these models with search-augmented reasoning, it's all really exciting.
It's a promising approach, for sure.
And the paper mentions some really cool future directions for this research, too.
They do, yeah.
What are some of the most promising avenues they highlighted?
Well, they talked about exploring more sophisticated search strategies,
Right.
maybe developing reward functions that go beyond just looking at the final answer,
Okay.
figuring out how to dynamically adjust retrievals based on how confident the LLM is,
Right.
using more than just standard web search, maybe bringing in different kinds of data,
Okay.
and even expanding these techniques to tackle things like multimodal reasoning.
So a lot of potential there.
Absolutely.
So for our listener, as you think about everything we've discussed today about Search-R1, I want you to consider the bigger implications. What does it mean for AI to be able to actively seek out and use knowledge as a core part of how it thinks?
Yeah, great question.
What new possibilities could that open up? How could it help us overcome some of the limits we still see in AI? It's definitely something to ponder.
It is, and if you're interested in diving even deeper, I definitely recommend checking out the paper itself and the related work we mentioned.
Absolutely. Great resources there. Well, thanks for joining us on this deep dive today. Until next time.